Right. So we have this characterization of Hardy space as if you're looking at LP functions of bounded support, then you're in Hardy space if and only if your integral is 0, if and only if you satisfy this cancellation condition. And the cancellation turns out to be critical. And so we did it in the case of one dimension, right? Our proof was only for the case of one dimension. And you remember what the difference was, right? The difference was that what we did was we took the set. So we had this thing, the truncated maximal function, right, which was defined to be the integral schema over balls containing a point. But the balls had to be a radius less than 1. And you took your average of the function over those balls, but only of balls with radius less than equal to 1. Okay, so you get this truncated maximal function, and the point was that we did a Calderon-Zygmunt decomposition on sets, the alpha. These sets where the truncated maximal function was large, right? Was greater than alpha, and then you use this thing to divide the function of interest into two parts: the good part and the bad part. Right? The good part turned out to be bounded. The good part turned out to be bounded by some constant times alpha, and the bad part actually is pretty good. It in turn could be split up into these little guys, each of which is supported on a you took this thing and then you decomposed it further into a union of open intervals. This guy's an open set. In one dimension, it's pretty easy to deal with open sets. Open sets are always going to be unions of disjoint open intervals. Okay, so you have this decomposition of the open set into these open intervals, right? And then in the Calderon-Zygmunt decomposition of your function into good and bad parts. The bad part can be further decomposed into parts, each of which was supported on one of those intervals, and further, the integral of each of these guys was 0. Okay. Okay. So this was kind of the key tool. In this proof, and where where we really use the one dimensionality of our case was here, right? To say that any open set could be decomposed into these guys, right? Okay. And so the problem, as we said last time, was to how do you do this in 2 dimensions, right? Do you have any sort of analogous thing? Do you have any sort of analogous decomposition of your set into open subsets? Okay. Remember how we used these guys. Not only here, this was sort of easy to get, right? These guys were easy to get. What we did was you took your function, you restricted it to the ball, and then you subtracted off the mean, right? Subtracted off the mean, and it gave it, and right, that's it, right? That's all you need. And then once you restricted it to the ball and subtracted off the mean, then the 2 conditions are satisfied, right? So that's sort of the easy part, or an easy thing to construct. Here is really where we use the set decomposition. What we did, you may recall, was notice that if you have x1 and x2, if your integral is x1, x2, then x1 so this is part of the decomposition of the sky, then x1 is outside, right? x1 is in the complement, right? So x1 is in e sub alpha complement, okay? Right? And that was good because that guaranteed us that if you took the integral over the closed interval, say, right? If you integrated over the closed interval, then you'd be controlled by some constant. Right? You'd be controlled by alpha. Okay, and that allowed us to get the bound on G. Okay. So you notice what you need. You not only need E alpha to be broken up into these sets, but you need these sets to be close to the boundary. Okay, you need these sets to be close to the boundary of E sub alpha. Okay, so that's so you have to think. Okay, well, in 2 dimensions, what can I do? What can I do to create an open set, to create a decomposition of open sets into subsets, each of which is close to the boundary in some sense. Okay, and so that's the motivation for this thing, which is a variant. Something called a Whitney decomposition. So Whitney. This is not really the Whitney. This is not exactly Whitney decomposition, but it's a variant of it. So it's something. The idea is based on it. Okay. So yeah. So before we get there. We'll introduce the notion of dyadic cubes. So something very simple, the notion of dyadic cube. The dyadic intervals, you start off with 0, 1, 2, 3, 4, 5. Right. These guys are your dyadic intervals. You take the closed intervals like this. Each of these guys of unit length is called a dyadic interval. Right, this is the zeroth scale, right? And then you scale them at all powers of 2. Okay, so you scale them at powers of 2 to the k as k ranges over the intervals. Okay, so right, the children of this interval are these half intervals here. The children of this interval, right, are these half intervals, right? And they're like the half. Right. The next guys, the children of those guys are like a quarter, et cetera, and going upwards, right? You have these guys of length 2, of length 4, of length 8, et cetera. Okay, those guys are called your dyadic intervals. And then if you take at any scale the product, at any fixed scale, you take the product, right? So 1, 2, right? 1, 2, etc. You take the product of these guys, and you get these guys called dyadic squares. You take the, in whatever, in n dimensions, you do this n times, and you get dyadic cubes. Okay? We call them cubes. They're also, this is not relevant at this point, and may never become relevant in this course, but they're also so-called dyadic rectangles. You take products of these things. And part of the problem in the product theory of singular integrals, where you're dealing with sort of like multi-parameter generalizations of this, is creating a Whitney decomposition that works for rectangles. Okay, so you got these things called dyadic cubes, okay, in n dimensions, and you notice that the radius, the diameter of these guys are all square root d times some 2 to the k, right? Where d is the dimension. Right? If it's 2-dimensional, then it's going to be root 2 times some power of 2, right? d dimensions, and your d times system power t. So diameters. Okay. And see, so one thing you notice is that if the interiors of any of these guys intersect, if the interiors of dyadic guys intersect, then that means that you're fully contained in one of the other guys, right? So if you have dyadic cubes intersecting, it's because one is contained in the other guy, right? Does anyone see that? It's because you are the child or grandchild of somebody that's bigger than you. So you never have something like this where you're intersecting multiple guys. Okay. So okay. So let me write a dilemma here. So given any open set, omega in RD, then omega can be expressed as a union of dyadic cubes with disjoint intervals, with disjoint interiors. So omega can be written as a union of dyadic cubes with disjoint interiors with the diameter of each cube being approximately the distance of the cube from the boundary. Okay. So that is, you can decompose this guy into cubes, but further, the cube, if you look at the distance to the boundary, then the diameter is going to be smaller than the distance to the boundary, and bigger than a quarter of the distance to the boundary. So this is the distance to the boundary. And, you're not gonna have anybody who is like this, a big cube that's close to the edge of the boundary, or a little cube that's far away from the boundary, right? Your diameter is roughly speaking the same as the distance to the boundary. Okay. And this is the encapsulation of the thing that we wanted. Right? We want this thing to be in a controlled sense close to the edge. Okay, so the proof of this is actually pretty straightforward. What we do is basically look at this condition. Okay, we look at this condition, and we just cover. For every point, we look for a dyadic cube that works. We look for a dyadic cube that's the right scale, and we cover each point. We cover each point with that cube. Okay. And then, to ensure that these guys have disjoint interiors, well, there's going to be too many of them. So to ensure that they have disjoint interiors, we just take the maximal cubes, right? Any cube that intersects another one intersects it because it's contained in that one. So just take the largest cubes, right? just take the maximal cubes, and then that will ensure that they're all disjunctive. So, so I mean that you could consider that the end, but let me just sort of sketch up what you do. You say, okay, for each x and omega, consider all dyadic cubes containing. Right? They have diameters. They have diameters of the form root d 2 to the minus k. Choose the one. So let delta be the distance. The distance of x to the boundary, x to the complement, and then you just choose qx to be the cube, such that the diameter of the cube is greater than 2 to the minus 2 delta and less than 2 to the minus 1 delta. So the picture is, right, you call this delta, right? And then you choose the appropriate one that has the rate, so that the distance, so that the diameter is bounded above by 2 to the minus 1 times delta, and bounded below by 2 to the minus 2 times delta. Okay, so you notice that, observe, the distance of the cube that we've chosen, so this is x, this is q sub x. The distance of this cube to the boundary, well, of course, is smaller than delta, right? Smaller than delta because x is in there, right? And delta in turn is smaller than 4 times the diameter of q sub x. Okay. Further, we notice that the distance of this thing to the boundary is bigger than delta minus the diameter of q sub x. Right? The distance of the cube to the boundary has to be bigger than delta minus the diameter of that, diameter of the cube. Which, by this thing, is bigger than delta over 2, which is bigger than the diameter of q sub x. And so, in other words, we have the inequality that we wanted, right? That the diameter that we've tracked the distance of the cube from the boundary to be between the diameter of the cube and 4 times the diameter of the cube. Okay, yeah, Mom.
Doctor, I choose this relation to be held. I chose the cube has this relation, right?
That's right. You choose the cube that satisfies this. So once you have these cubes, then you just take the maximal cubes, and that gives you the decomposition that you want. Any questions? Okay, so once you have the once you have that decomposition, then you do the Cadwan-Zygmunt decomposition in basically the same way. You say, okay, we're going to let G be f times the characteristic function of the complement of alpha, right? Plus the sum of the averages over each cube, right? Where m sub j is the actual average of the function of the cube, right? And you let v be the sum of b sub j's, where each b sub j is the function minus its average over as the characteristic function of the cube. Okay, so to see how this gives us the desired control over the average, right? We need to see we see then that that the absolute value of the averages is controlled by C alpha in the following way. We say, well, look, right? Here is E sub alpha, and here is our cube. Okay. You choose some ball, choose a ball B that contains Q and has radius that's 5 times the diameter of Q. 5 times the diameter of Q. Being a radius 5 times the diameter of Q ensures that you are going to intersect the complement, right? By our construction. So remember what we did last time. If the ball is of radius greater than 1, then we're basically done by our. Remember we made those assumptions about the L1 norm of the function, right? So in the case the radius of the ball exceeds 1, then we're done by our assumptions. So remember we broke it up into two cases. For the big guys, it was immediate that we were done, right? Because the L1 norm was less than 1. If the radius the radius of the ball is less than 1, well then, you say, well, okay, let's look. Let's look at the average. We know the average is, we know that the average of the absolute value is controlled by the integral over the ball. Right? Because it'll just get bigger. The ball is bigger. Right? And we know that that is controlled by the average of the ball. The average of the ball times some ratio. Right? This average of the ball, right? This ball contains some point which is in the complement. You know, is where the maximal function is small. Right? So we know that this is controlled by this ratio times alpha. And now you see why we really need the ball. We need the cubes to be of a controlled distance to the boundary, right? Right, because we want the ratio of b to q to be some sort of controlled number, right? So this is controlled by some constant times alpha, right? Because we've chosen the ball to be 5 times the diameter. We don't want to have some sort of tiny cube here and a gigantic ball, because right? then that constant is not controlled. Okay, so that gives us control over the mean, right? That gives us the control over the mean on. And that is to say, that gives us control over the over this part of the good function. Right? And then from there on, you proceed basically the same way. Okay. The rest of the proof is basically identical. Okay. So this is the first observation that we make after the proof of the characterization of LP functions of bounded support that are in Hardy space. Okay, that it's possible to extend it. It's not difficult to extend it to higher dimensions as long as we have a way of decomposing open sets into these things each of which is not as control. Each of which has a diameter that is proportional to its distance to the boundary. So that's the first observation. Everyone all right? Okay. So okay. And the second observation is something about the atomic decomposition itself. So when we defined our atoms, right? We said, okay, A is an atom associated. So recall. A is an atom associated with a ball. B, if like the L infinity norm of A is controlled by 1 over the size of B, and 2, the support of A was contained in B, and 3 satisfied its cancellation condition. Right? So these were this is how we define the atom, and the way we defined H1 was as functions, as L1 functions that could be realized as linear combinations of atoms. Okay, so this is sort of a weird. I'm not sure how you define H1, but probably not this way. But you probably you probably defined H1 in some other way, and then maybe show that all H1 functions had an atomic decomposition. In this text, sort of backwards in a backwards manner, we're defining H1 via the atomic decomposition. Okay, saying you're in H1 if you're an L1 function and you can be realized in a linear combination of atoms. Okay. So okay. So that was an atom. Really, this is what's called an L infinity atom. Or I guess they call it an infinity atom. So the second thing we're going to notice is that, in fact, we could have used LP. So from the proof, we'll follow some, we'll gain some insight that will show us that, in fact, we can it's okay to use certain variants called P atoms. So given a measurable function A supported on ball B, if the LP norm is controlled by this MB to the -1 plus P, and your support is in there and you satisfy the cancellation condition, then we say A is a P atom. A is a P atom, and what we're going to see is that the atomic decomposition could have been carried out using the P atom. And you could have defined it using the P atom or whatever fixed P atom you like. Okay. So here's the corollary of the previous theorem, the characterization theorem. Any P atom is in H1. Further, there exists a bound independent of atoms independent of the atom such that the H1 norm of every atom, every P atom, is controlled by that number. So all P atoms have an H1 norm bounded by some constant. Okay. So we start off by making some observations. So observe if A is a P atom, on a ball B of radius r, say, if we define a sub r x to be r to the d a r x, so this is the dilation of a to the 1 over r scale. Then we see that a sub r is supported on 1 over rb. And further, right, that is to say, Rx has to be in B, right, of course. And further, we notice that if you do the calculation and look at the if you look at the LP norm of the dilated guy, what you get is R to the D minus D over P times the LP norm of the original guy. Okay. Which, by assumption, is controlled by right, the LP norm is controlled by the measure of B to the minus 1 plus 1 over P. But that, in turn, equals, if we put that all together, that's 1 over R to the D, the measure of B to the negative 1 plus 1 over P. So what I'm saying, well, right, that's to say the measure of 1 over R B to the negative 1 plus 1. So the point is that that the dilated guy is still an LP atom, right? Because it's supported on 1 over RB. Its integral is still 0, and its LP norm satisfies the condition, right? Its LP norm is controlled by the measure of the ball that it's supported on to the negative 1 plus 1 over P. So, the point is that A sub R is still a P atom. And further, it has the same H1 norm as A. Is that obvious? So it still has the same H1 norm as A. The H1 norm we get by taking atomic decompositions. Right? So you have this guy, you have A. If A has an atomic decomposition, then you just scale that atomic decomposition, and you get an atomic decomposition of AR. And that atomic decomposition will have the same constants on it. Right? So then, when you take the infimums over all atomic decompositions, you're still going to get the same H1 norm. So this guy has the same H. If you start off with a P atom, if you scale it, it's still the P atom, and the H1 norm is still the same. So this observation is useful because so this set of observations. So this is the observations right here. So observe this, and then that allows us to say, well then, without loss of generality, if we're trying to get a control on the H1 norms of P atoms, we can assume that the P atom is supported on all of unit vagueness. So that's the point of this calculation here. So without loss of generality, thus without loss of generality, we may assume to be without unit vagueness. I had a professor in college who was a very clever guy, and at one point, as I recall, he arranged his lectures so that at one point it would end up that it was either be or it was not to be. It was be or not to be. Or it was to be or not to be, I think. Anyway, this guy was an older guy, you know, and he would come in and he would look at the board, what was left from the previous class, and then he would selectively erase. So if there was like an equation here or a graph here, you might leave some of it there. And then he'd start his lecture from the left side of the board. And as he reached the things that were left over from the previous class, he would incorporate them into his lecture. And yeah, he was, and we would all cheer. Anyway, so without loss of generality, when we assume B to be of unit radius, but then notice that then if we look at the L1 norm of A, that is controlled by the LP norm of A, right, by Hilbert's inequality, right, times some constant, where the constant is 1, right, so by Hilbert's inequality, and by the first assumption, this is 1, right, because B is a unit radius. Okay, so right, so this is an L1 function, right? This is an L1 function, and it satisfies the cancellation condition, right? This guy is in H1, right? By the previous theorem. The previous theorem said that as long as we satisfy cancellation, and then we're good. We're in H1. Sorry. So what's the H1 norm of A? What's the H1 norm of A? Well, if you go back and look at the proof, so if we examine the proof of the previous theorem, last class's theorem, what we see is that the H1 norm of our function, I don't know if you remember this, but it turned out to be controlled by the L1 norm of the maximal function, right? The L1 norm of the restricted maximal function. Right? You remember in the end, we were integrating over these, over R, over 0 infinity, some distribution function, right? And that turned out to be bounded by the distribution function of F dagger, in fact, right? So that turned out to be controlled by the L1 norm of F dagger, right? And the fact that this was bounded by infinity gave us that our guy was in L1. Right? So what you see from that is that the H1 norm is actually controlled by this thing. And if we look at this thing, this is controlled by some constant times the LP norm of F dagger. Right? The reason was, you recall, that this thing was supported on the ball of three times the unit radius, right? 3 times the radius, and so you could use Cauchy-Schwarz again to get this bound, right? This thing was supported on the ball of triple radius. Okay, and so you get this thing, and then what happened was that we bounded this using the LP boundedness of the maximal function, of the original Hardy-Littlewood maximal function, which is bigger than this guy. Right? The Hardy-Littlewood maximal function dominates the truncated guy, and the Hardy-Littlewood maximal function is bounded on LP. Right? So this is bounded by the constant, the LP norm of the Hardy-Littlewood maximal function times this constant times the LP norm of F. Right? Which for us, thus we see that the H1 norm of this guy is bounded by some constant times the LP norm of the Hardy-Littlewood maximal function. Okay. Yeah. And just as a side comment, this constant, MP, is of order 1 over P minus 1 as P goes to 1. Okay. So that gives us the control over the atoms H1 norms that we're aiming for. And the point is that so that's the end of the proof of corollary. Okay. The point of the corollary is this, right? If F can be expressed like this, where the A sub k are p atoms, these guys are p atoms, then the H1 norm of F is controlled by this constant times the sum of the FC values and constants. Right? And further, you can go the opposite way. And if F is in H1, we have a decomposition of F in P atoms. So if you have a P atom decomposition, then you are actually in H1. If you're in H1, you have a decomposition in terms of P atoms, because the infinity atoms are all P atoms. Right? Because the infinity atoms are P atoms for all P. Okay. So what this basically says is that we could have defined H1 in terms of P atoms, and we would still get the same norms. We would get equivalent norms. Okay, so there's nothing particularly special about using infinity atoms, and sometimes it makes more sense to use P atoms for a particular P. Okay. So this is, these are the two observations we make after the characterization. So, any questions? Any questions? So now let's do something pretty nice, which is to show that the Hilbert transform actually behaves nicely on H1. So that is to say that party space really is the proper replacement space for L1 in this context. Okay. So boundedness Hilbert transform from H1 into L1. So here's the statement. So let F be a party space function, and just in R, right? Because our Hilbert transform is only defined in one-dimensional case. Then H sub E F is in L1R for all epsilon greater than 0. Okay. And you see right here, this H1 guy is the truncated Hilbert transform. So it's so you convolve with 1 over t. You convolve with 1 over t, but you chop it away from the origin. Okay. You chop it away from the origin. You recall this. Okay. Okay. So we're going to show what we showed earlier. You recall we showed earlier that HEF converges to HF in L2. And that's how we showed that, recall, that's how we showed that the Hilbert transform was a principal, was a singular integral, could be realized as a singular integral in this sense. Okay. Okay. So these guys all turn out to be in L1. Further, HE converges in the L1 sense as that one goes down to 0 to some limit, which we call HF. So which we call HF, and such that the L1 norm of this limit is bounded by some constant times the H1 norm of F. Okay. So these guys converge in L1. These guys converge. Like if we look at them in for F in L2, these guys converge to the Hilbert transform that we had earlier. Right? If we look at the behavior for F in H1, they converge to something that we call the Hilbert transform, and that thing is bounded on H1 to L. Okay. So it's in this sense that the Hilbert transform is bounded from H1 into L1. Okay. So the proof. Let A be an atom. We'll make a couple of observations. So we'll first show show that for H epsilon, the L1 norm of H epsilon A is controlled by some independent constant. Okay, and then we'll use this fact to put it together for the general H1 function. Okay, so the first thing, we first make some observations. First observe that if you recall that we called A sub r we define to be R A R X. D is 1. Okay, so this guy is the dilation, right? Something sub r is denoting dilation for us. If we look at, so it's a calculation to see that H, if we apply the Hilbert transform to the dilated line, what we end up is the dilation of the Hilbert transform of the guy. Okay, so that is to say, you can either dilate it in the Hilbert transform, or you can Hilbert transform and then dilate. Hilbert transform commutes with dilations. So it's a calculation. Second thing to observe is that the Hilbert transform also commutes with translations. So it suffices to consider atoms supported on a unit interval centered at the origin. So on a unit interval centered at the origin. Or if you don't like it, you can just go through the proof and see that it works. You can see that it works if you in the general case. Okay, so what we're going to do is right, we want to control the L1 norm of this. We want to control the L1 norm of this guy, and we're going to do something that you may see many more times. You may see a lot of this. So we'll estimate. We're trying to get the L1 norm. L1 norm of the truncated Hilbert transform applied to this atom, and we'll estimate it in 2 parts. So it's sort of like a local part and a global part. Okay. Local and global. And each part will turn out to be controlled by a different facet of the Hilbert transform. Okay. The local part, what will be key here is the L2 boundedness. What will be key in the global part will be 2 things. One is that the smoothness of the kernel 1 over t. And the other thing that will be key is not about the Hilbert transform, but about the functions that we're applying to it. That the function satisfies a moment condition, a cancellation condition. Okay. So it'll be the interaction of the smoothness against the cancellation that allows us to control the global part. The local part will be controlled easily. The global part is controlled by this interaction. Okay. And this is sort of like a common theme. This sort of thing will occur again and again. Okay, so let's do the local part first. Looking at the part that is small here, looking at the local part here, we see by Cauchy-Schwarz that this is bounded by some constant times the L2, right? We want times the L2 normal of this thing, but we know that those guys are all bounded by some constant. Right? All those guys, all the L-infinity atoms are in L2, so with some constant L2. So controlling the local part is just a matter of invoking the L2 boundedness of the Hilbert truncated Hilbert transform. Now the other part is a little bit more tricky. It's a little bit more tricky. So this is the local part is the easy part. The local part is the slightly tricky part. Okay. So for x size bigger than 1, you say, okay, well, let's just look at the let's look at this thing. This is 1 over pi times the integral t greater than or equal to epsilon. A x minus t dt of t. Right? You can change the order of the convolution. Right? That is to say, you do some change of variable, and you get x minus t greater than epsilon. So you get a change of variable. Make it look like this. And then we play the cancellation trick. We say, okay, we can, since the integral of a is 0, it's okay for us to slide in a 1 over x. Then noticing that if x is bigger than 1 and t less than a half, which we do know by our assumption about the support of a, we get this thing is controlled by 1 over x squared. So what that gives us is that, so we get that this thing, right, is controlled by some constant over x squared, for x bigger than 1. So what that gives us is that, thus, if we look at the global part, the integral over x bigger than 1, we get that this is controlled by 2c. Right? Because we're integrating c over x squared, we're integrating c over x squared over over this interval. So that's how one gets the global part, and so putting 1 and 2 together, right? 1 and 2 together give us that the L1 norm of these guys is bounded by constant for all atoms. So that's the first move. Okay, so I thought we might be able to finish this today, but I think we will stop. We'll stop here. So we'll finish this up. So, right, so you know, you see what's going to happen, right? We're going to ultimately, you know, we're going to use the atomic decomposition of functions in H1. We've got the result. We're getting the result for the atoms, and then we'll put it together to get the results for the general H1 functions.
You go from that step to that step.
From here to here?
Yeah.
So this is by the cancellation, right?
You add and subtract a 1 over x. And since the integral of a is 0, this goes to 0.
Right. Right, but something is bugging. Hold on. Something's not quite right, right? Is that right? So if this were like this, then it's maybe believable, right? Right, because the integral of a is 0, right? The integral of a is 0, so we're just sliding in some constant times 0, right? 1 over x times this integral is just 0. Right, so it's okay to add this thing on, right, because this is 0.
Okay.
Right, but what about this? We're integrating over, right? So x is away from 1. This is out here, and t has to be more than epsilon distance away from. T has to be more than epsilon distance away from epsilon. T has to be more than epsilon distance away from there, right? And we're integrating over this thing, right? Which is okay because A is supported on 1/2. So this is okay for T small. Okay, so I should have said here T small. Yeah, thank you. Yeah, you caught something. Yeah, so T has to be small enough that this thing covers the this thing covers the support of A. Because then we're integrating a support of A, which, and we do get 0.
Yeah.
Thank you.